Here we're going to review the basics of EIGRP. We'll do a classic EIGRP configuration and look at how it behaves. Enhanced Interior Gateway Routing Protocol, or EIGRP, is an advanced distance vector protocol. Its administrative distance is 90, and remember, administrative distance comes into play when you have multiple routes to the same destination via multiple routing protocols. So I have the same route to if I can get to the same route while using multiple routing protocols, then I'm going to choose the route with the route from the protocol that has the lowest administrative distance. It's considered more trustworthy. So if I have a RIP and an EIGRP route that both go to 192.168.2.0, I'm going to use the EIGRP route because it has a lower or better administrative distance. EIGRP uses a composite metric to make its best route decisions. The metric is made up of bandwidth, delay, load, and reliability. However, when you leave everything at its default, it becomes made up of simply bandwidth and delay. So the default metric is bandwidth and delay. It uses multicast address 224.0.0.210 for IPv4 to do exchange routing information, and it uses FF00::A to exchange routing information in IPv6. It supports variable length subnet masking, and rather than using UDP or TCP, it uses Reliable Transport Protocol, or RTP, to exchange its routing information. So when we looked at RIP and RIP v6, it uses what, 520 and 521, UDP 520 and 521 as its protocol, as its transport. Instead, EIGRP will use RTP to exchange that routing information. EIGRP also does load balancing, and we can also configure to do unequal cost load balancing, and we'll do that later. EIGRP maintains 3 tables: the neighbor table, which contains all the routers that it's formed an adjacency with. So basically all its neighbors, right? If it's formed an adjacency with the router, it's its neighbor, and so they will all be in the neighbor table. The topology table consists of all the routes advertised by its neighbors. So if I'm sitting on R1 and it's connected to R2, R3, and R4, and they've formed an adjacency, meaning they agree on things, for the most part, that's going to be, in our classic configuration, that's going to be autonomous system number for sure. Then R2, R3, and R4 will show up when I do a show IP EIGRP neighbors. R2, R3, and R4 then will also let R1 know about all the routes that it has. Okay. And all of those will be maintained in the topology table. And then dual takes the topology table, or takes all of those routes, and calculates the best routes. EIGRP uses dual for route calculation, or best route calculation. So inside that routing table, our third table, are the best routes to each destination, also referred to as the successors or successor routes. By default, up to 4 successor routes can be in the routing table if each route has the same feasible distance. So next we're going to kind of look at feasible distance, reported distance, and specifically as it pertains to a backup route. Successors are the best route to the destination, whereas feasible successors are the backup route maintained in the topology table. So let's just kind of draw it. So let's go ahead and I'm going to try to draw some routers. You should know early on I'm not much of a drawer, but hey. So we got router 1. He's connected to router 2. Right. And he has a network over here. Let's say R1 is also connected to R3. And he's also connected to this network somehow. And we're going to call this network the 192.168.3.0 network. Okay, we're going to sit on R1. He's our local router that we're going to deal with right now. Whoops, sorry. All right. So R1 needs to calculate its best route to the 192.168.3 network. Its neighbors are both reporting routes, right? Because they're both connected. R3 and R2 is reporting a route. Those routes will be in the topology table. R2 will report its distance to get to the 3.0 network. That's called reported distance. So when he sends an update or an informational or whatever you want to call it, he reports his distance to the 3.0 network. Okay. Whatever R2's distance is to this network, right, is sent to R1. R1 then adds the distance from itself to R2, right? Because then the complete metric or distance, I keep referring to distance because it's feasible distance, reported distance, metric, right? The complete metric to get to this network is what it is from R1 to R2, and then what it is from R2 to 192.168.3.0. So it takes the reported distance as reported by R2, adds the distance between itself and R2. Okay, that's the whole metric. R3 will do the same thing. It'll say, hey, R1, here's my reported distance to the 192.168 plus, wow, 192.168.3.0 network. R1 will add the distance from itself to R3 to that and come up with that metric in order to get to 192.168.3.0. At this point, we have two metrics, or two routes, that both have metrics to get to that 3.0 network. The lowest of those metrics is considered the feasible distance. If those metrics are exactly the same, they have the same feasible distance, they'll both of those routes will be in the routing table. Okay. Let's say that, I'm going to erase this for a second. Darn it. Oh, forgot about that part. Forgot that when I erase all instead of part, I'm going to erase everything, right? So R1, R2, let's do R3 again, and we're going to do our 192.168.3.0 network, right? And they both have. Let's say that R2 reports a distance. It will report a distance, right? And that should be in the topology table. Or that route will be in the topology table. Whoa, as described by R2. R3 reports a distance. Fine, let's say the reported distances are exactly the same to actually get to this network. However, let's say the bandwidth over this link right here is really, really bad. It's really low. So then what happens is when R1 adds its metric to get from itself to R3, the feasible distance here, the metric here, the composite metric from 1 through 3 to the 192.168.3.0 network becomes greater than the metric from 1 to 2 to the 3.0 network. This metric, then this lower metric, becomes the feasible distance, and since this one is higher, only this one, this here, will be in the routing table. Now, how do we figure out if, in fact, this guy, even though it doesn't have a very good feasible distance, or it's not the best feasible distance, could have a good feasible distance, could be a backup route? It has to meet the feasibility condition. The feasibility condition says if the reported distance is less than the feasible distance, then the route can be a backup route. Okay? And remember when I was just explaining it, I said the reported distance here and here, the distance that R2 reports to R1 and the distance that R3 reports to R1 is the same. Okay? So this guy can become a backup route because its reported distance will be less than the feasible distance, than the total feasible distance. Because what changed up here to make this feasible distance greater was the bandwidth here. It wasn't the reported distance that changed, it was the bandwidth. So the reported distances are the same. We added this local piece, and that's where our feasible distance has changed. Maybe to look at it, even though I really didn't plan on going, I'm going to go through this again later when we look at variance and stuff, but the feasibility condition says that the reported distance is less than the feasible distance. In our example, it would be, which means that the best route is the route from R1 to R2 to get to 3, but the backup route would be from R1 to R3 to get to the 192.168.3 network. And the reason why, of course, that EIGRP maintains a backup route is because, I'm going to just erase it, is because it's faster convergence, right? If I've got my routing table, and I've got my topology table, and I've got a route to the same destination in each one of them, let's say this route goes down. Let's say R2, well, R2 dies, right? So it goes down for whatever reason. Right away, my route through R3 to get to that 192.168 network can go into my routing table instantly. If for some reason, let's say if I had drawn the picture differently, and R3 went in through R2, and that made the reported distance greater than the feasible distance, then this would have never been in the topology table, which requires EIGRP to query its neighbors to try to find a backup route, or to try to find a route, because now its route went down. It didn't have a backup route in the topology table because any additional routes that we had didn't meet the feasibility condition. So now the route went down, EIGRP has to go ahead and query its neighbors to try to get a route to that destination. All right, let's go ahead and look at our configuration next. So configuring it is pretty easy. Classic autonomous system. I'm going to guess 1,000 times you've already done this, especially in the entry level stuff, right? The CCNA level stuff. But we'll do it again anyway, just to review. So router EIGRP and the autonomous system number in global config, and if we want them to form adjacencies, the autonomous system number has to match. And then we do the network statement, and the network statement's used to activate the interfaces that will participate in EIGRP. And then we can assign a router ID. We don't have to. It will find one because it has to use, EIGRP has to use a router ID to identify the router in its EIGRP information that it exchanges and whatnot. But I could configure a router ID using the EIGRP router ID command, and then the form of the ID is the same as an IP address. If I don't configure a router ID explicitly, then the first thing EIGRP will do to try to find an ID will be to look at all your loopback interfaces. If you have loopback interfaces, it will use the IP address, the highest IP address of your loopback interfaces. If you don't have any loopbacks, then it will use the highest IP address of your active interfaces. So it will find one if you don't configure it, but you can configure it. Let's go ahead, and here's our topology. I've got 4 loopbacks configured. I don't really have computers, I just put these pictures just for visualization. I have 4 loopbacks configured, 0, 1, and 2. 0 has an IP address of 10.1.1.1. 1 has 2.1, 2, 1. 2 has 3.1. And then I have serial links between branch 1 and HQ and branch 2. They're in the 192, this one's in 192.168.1 network. This one's in 192.168.2 network, and then I have another loopback off of branch 2 that's in the 10.1.4.0 network. So let's go ahead and do classic configuration. It should be pretty easy. I'm going to switch over real quick. All right, starting with branch 1. We already looked at the commands, right? Remember, it's router, EIGRP, and then an autonomous system number. You can use autonomous system number 1. And here what I want to do, the network statements only activate the interface to participate in EIGRP. So I'm going to use a quad 0 address in order to, or network, and that will activate all the interfaces to participate in EIGRP. And really that's it. That's all I have to do. So I'm going to go ahead and let's repeat that on HQ and branch and see that EIGRP will then work. All right, over here on HQ, config T, router EIGRP and autonomous system number. Remember, I want them to form a neighbor relationship, right? So we've got to use the same autonomous system number. I want to activate all interfaces in EIGRP, so we'll use the quad 0 network statement. And let's go back, and you can see that our adjacency came up. And I pulled over branch 2, and on branch 2 I did something real quick I want to take out. I just had it in there from earlier. I have a no logging console enabled, but I want it to log to console because I want to see the adjacencies when they come up. So we'll do that first, and then do router EIGRP 1 network 000, enter. All right, now he's formed an adjacency also. So branch has formed its neighbor adjacency with HQ. HQ has formed it with branch 1, so we should be good. If we do a, let's do a show IP. Let's get rid of the logging console first again, okay? Because I don't want to see that right now. No logging console. And that's just so that I don't end up with stuff like this while I'm doing, while we're doing configurations together. Okay, now, show IP EIGRP. Let's start with neighbors, right? That's our first table. As EIGRP tries to build its overall topology and its best routes to its destination, it starts by building a neighbor table. This is a list of all the neighbors that branch 2 has, and in fact, since the only thing it's connected to is HQ, it does only have this one neighbor. So our neighbor table looks good. Let's do a show IP EIGRP topology. Oh. Okay. These are all the routes. These are all the routes that branch 2 learned from HQ, right, from its neighbor. Topology table contains all the routes learned from its neighbors. Since it only has one neighbor, then these are all the routes that branch 2 has learned from HQ. And it learned about the 2 network it's already directly connected to. It learned about 10.1.30, 10.1.20, 10.1.10, right? Because HQ knows about those routes because it got them from branch 1. So these are branch 1's routes that HQ let branch 2 know about. So the topology contains all of our routes. Now our routing table contains all of our best routes. So if we have multiple routes to the same destination, remember the one with the best feasible distance will be put in our routing table, or the best metric will be put in our routing table. So show IP route. Okay, and these are our routes too. So D signifies it's using EIGRP. C is connected. So those are all our directly connected routes. So branch 1, its best route to get to 10.1.10 uses EIGRP, and it can get there via 192.168.2.1. In brackets here, the first part is its administrative distance. Comes in handy when we get further through the course and we talk about redistribution. And it's feasible distance, which will come in handy when we have multiple routes to the same destination. Okay, so let's go back. Let's do a show IP EIGRP topology again. And the only thing I want to show you here is this first number is feasible distance. The second number is the reported distance of that route. So how is it reported to me? Then I added the metric from myself to the router that reported it to get feasible distance. Again, that'll come in handy later when we look, for example, on unequal cost load balancing. Okay, so that's pretty easy. Now let's say that we didn't necessarily want all of our interfaces to participate in EIGRP. Maybe we just, maybe we wanted to not have 2 of these participate. I'm just throwing it out there. I don't know why. I don't want these 2, so I only want this one and this one to participate in EIGRP. Maybe I want to hide these in my internal LAN. I use some sort of default route or static route for these guys to get out. So that means I have to configure EIGRP a little differently, right? So let's go back and do that configuration. We'll go over to branch 1 and change this. So now in branch 1, we only want to advertise what we see, the 10.1.3. Well, we're not advertise. We only want 10.1.3 to participate and 192.168.1 to participate in EIGRP. So first we do a no network. And instead we'll do, we lost our adjacency. Totally makes sense because right now our directly connected interface isn't participating in EIGRP. So our adjacency went down, whoops. Network, so let's put that one in so at least we get our adjacency back up. So we do network 192.168.1.0. It's classful, we don't need a wildcard. Now our adjacency came back up. Let's do a show IP route. Spell it right first. Okay. Here we still have, we have all the same routes, right? Because it's about what we're advertising, not what everyone else is advertising. So right now, we have our connection to HQ. HQ is telling us about branch 2. Let's do this first. Let's ping 10.1.4.1. Let's just ping that. Okay. Now let's ping 10.1.4.1. from a source of 10.1.1.1. And it's not working. What's the problem? Right? Thought about it? Let's go back at our picture. If we look at it, branch 1, whoop, that's a real pen, that's not going to work. Branch 1 has a route. It knows about the 10.1.4. It's in the routing table, right? Didn't we just see it in the routing table? Pretty sure we did. So the ping is going to get there. However, if we look at this routing table, boy, I hope I'm right. It's the worst part about demonstrations sometimes. This guy doesn't know about the 10.1.1.0 network. So in fact, the response is actually what's not getting back, or that should be the case. Let's go see. So let's do a show IP route in branch 2. Right. And in fact, what we thought was true was true. We have no routes now for 10.1.1.0. So our ping is, it knows where to go, but when branch 2 has to do the echo response or has to respond to that ping, it's going to die because it doesn't know how to get to the 10.1.1.0. That's why it worked perfectly fine to get to 10.1.1.4 the first time. The reason being is, if you remember, and if you don't, I'll remind you, I guess. I gotta stop saying if you remember. So the first time we just straight up ping, right? Ping 10.1.4.1. When it does that, it uses closest outgoing interface, right? And the ping got here with a source in the 192.168.1.0 network, which branch 2 had in its routing table so it could respond. When we used a source of 10.1.1.1, it went out because I still have branch 1 still has a route to 10.1.4.1, but it couldn't get back because when it had to return, what was the destination? 10.1.1.1, and branch 2 didn't know anything about that network. Okay, so you could do static routing or default routing or something like that. Let's go back and do something else real quick. So let's say we don't want to do static routing. We don't want to do default routes. We want to actually want 10.1. We want to have 10.1.1 participate. Actually, let's say we want to have, let's do 10.1.1. So, and all you do, right, is router. Now what I want to do is, because I want to be very specific to the 10.1.1 network, I'm going to add a wildcard. So I'm going to do network 10.1.1.0, and then my wildcard will be 0.0.0.255. So now I'm allowing just that interface. Actually, in particular for our network, it's that loopback 0 interface. He'll be allowed to participate in EIGRP, or he's activated to participate in EIGRP. So let's do a show run. And what I should have done, I didn't. I'll show you in the next one. All right, so our interfaces that are participating are, this is our loopback 0 interface. This is our serial 00 interface. Now, let's go over to branch 2. Show IP route. Whew, yay, like I said, 10.1.1.0 is now in there. So now if I do my source ping, it should work. I'm sure you guys have already noticed I say it should a lot. I don't know how many times I've done demos and all of a sudden I'm like, oh, wow, that didn't work. Usually it involves troubleshooting. So we'll ping 10.1.4.1 with a source of 10.1.1.1. Perfect, and it worked this time. We were successful. So I think that's it for this one. This one's plenty long enough for you. We did classic EIGRP configuration with the autonomous system, looked at a couple different ways to activate interfaces into EIGRP and kind of looked to see what that entailed. And one thing to keep in mind is in iOS 15, EIGRP auto summarization is disabled, so it always sends the subnet mask. So when I do something like this where I have the 10 network on both sides, worked perfectly fine here. If I have a version of the iOS prior to 15, auto summary is enabled, and you're going to have some issues because HQ will see branch 1 and trying to get to branch 2 will see a 10 network. They'll see them both, and they'll both think that they can actually get there. That discontiguous summarized network issue. All you have to do is turn off auto summary, but something at least that I notice sometimes students working in labs is that they forget that when I do my demonstrations, auto summary is already off in iOS 15, and all of a sudden they're working on a previous iOS and they have issues with the same topology, and that would be why. Anyway, that's it.